Hello everyone, my name is Mohammed and this is my second progress video for my computer technology project. Uh, and let's just get into it. Alright, so what I've completed so far is I've had a broken PCB and I started reverse engineering it. How did they create this time ignition module back in 1982? The other thing that I've done or I've looked into quite a bit was the component selection. I've learned a bunch of different styles of DC to DC converters, and I started to learn the Altium Designer and PCB. And let's go on the component selection. So, the basic three components at the highest level that I'm going to be using is a FPGA. So I've chose this one because I already had it, which is the Altera Cyclone 2. It's an older chip, but that can do like 50 megahertz. But I'm pretty sure you can throw a higher clock cycle, just get a little bit hotter. But generally, 50 megahertz is pretty good. And because it's such an old module from like 2012, it's good enough, it's cheap, and I can start designing a whole circuitry around it. And as you can see, the one I have here it's a minimum systems board. So there is absolutely no peripherals. So all I have here is I/O pins, and I can connect it directly to a breadboard and actually use it straight away. So that's the nice thing about it. And I'm pretty sure this whole design is referenced online, so I can actually mimic it when I go into Ultimate Design and creating my final version. Now, this is kind of the old broken board that I was talking about, and I've kind of looked at how it works. So, the main idea of how it works is pretty interesting, actually. Um, it has a bunch of capacitors in varying sizes to actually filter out for the 12 volt down to a 5 volts. And down here, um, there is actually a HIC module, which is which from what I can understand is a microchip that is a memory module that just pulls the right memory and triggers either one of these PNP transistors, which are Haltech transistors, and Haltech is a famous automotive brand, like electronics brand for sensors and stuff. And you can see here that they've annotated actually quite well. So you have the BCE, the base collector and emitter. So reading the actual board was like in terms of power, in terms of its power distribution network, and how they used these components was really nice, as simplified it for me. As all I need is to find is a transistor that matches or beats the specs of this one. Now the last bit of it was I thought it would be cool to have a PL and PS side. So PL PS side is from my internships. What I've learned is you can have a PL, which is processing logic, which is the FPGA, and PS, which is processor, which is the CPU side. And you can have you can use that FPGA as an accelerator or an interfacer. The interfaces were all modules, and still use C for the other high level stuff. And because I chose an ESP32, it would be nice to actually have a little bit of networking and IoT devices within it. So it will feel a lot more like an IoT project and like a whole like modern ECU system. And yeah, so that's kind of like what I've done so far. All right, whoop, too much. All right, the next thing is we're learning about different DC to DC converters, and I was testing out different types of circuits. And last time I looked at how power supplies in computers actually do like power filtration and making power distribution networks. This time I actually looked on the motherboard itself. So with on the mother, I had a very old motherboard, and I was looking at the yesteryears of technology. And there's this one section of the motherboard called the VRMS, uh, and that whole section is just capacitors and logic to actually step down from 5 volts all the way down to a single volt or even less. But because I had a really old motherboard, it was stepping it down to a single volt. And I was looking about the coils and how they would generate the PWM signals. And I started looking at online resources, and I learned that probably a voltage regulator that's already pre-made is probably best suited for my application than trying to create one that is like a PC. The reason for that is when you're creating a DC to DC buck converter, is you need to actually know the maximum load and the minimum load. As within the graph here, if you get close to the maximum load, it will exponentially go up and saturate. Same thing when it goes down. So you have kind of like a Goldilocks zone between this point and this point of actually generating it. And that depends on the duty cycle, how many windings on the coil. It becomes way too like complex. And uh, and this is kinda like how on a on a very small voltage, like if you zoom in on the voltage over time, this is the kind of the voltage ripple. It's always a triangle, and depending on the duty cycle, you could have it more to the you can have a try the power in signals to be more to the left or more to the right. So so it really depends on everything. Even though I've learned quite a bit about this, I ended up just going with off the shelf just because it was simpler, and I don't think I can get a really good system or like really reliable system just from scratch, or I'm gonna run out of space on the board itself. All right, so that's kind of what I've researched so far. That's power distribution completely done. I've kind of have a solution now. I have to move on to the actual making the logic and component selection and creating the PCB design itself. Now, learning all that's the next step is learning Altium Designer, and we gotta learn. I'll just talk about it a little bit. So, Altium Designer is a software. It's usually called an EDA CAD tool, and it's nice because it has a bunch of functions and systems that you can customize to actually customize to your requirements to do like board analysis and yeah. So the first thing I did was just follow their online like kind of school or units that they have on Altium website. And there over there is what I learned for a Gerber file. Gerber file is just the PCB. So how big is it? Where the trace is that multi-layer board? And that's what a Gerber file describes. And it's kind of like a STL file, but for like manufacturing. Now, the other thing I learned about within LTM is that is really neat is the schematics. So you, while designing the board, you can actually create schematic sheets of like what is connected to what. So this one connected to 5 volts, this is connected to blah blah blah, and you can keep track of it within one software rather than just drawing it on a piece of paper, as what I've been doing, or spending quite a bit of time on Draw.io. And I've also learned how to render the PCB itself. All right, so pretty short presentation for today, but that's because I'm still in the midst of researching all the uh, big modules that I definitely need. And yeah, the next milestone would be um, is actually asking because now I have a really clear understanding of how the PCB will look and how all the chips come in together. But the one thing I still don't know is um, like rules of thumb. How do I protect the actual FPGA and all the chips? And yeah, within my next project, I would have talked to some engineers and ask them their opinion about it. All right, thank you for listening, and I'll see you in my next video.